Hello everyone, welcome back to another tutorial for the course Social Network Analysis. In today's lecture, we'll study how we can basically represent graphs and nodes in a computational manner. So we have already seen the theoretical side of it. We have learned various algorithms like DeepWalk, Node2Vec and GCN, etc. In today's class, we will be learning how can we use these algorithms in a coding manner. So we'll start with DeepWalk, then we'll go to Node2Vec. Further, we'll see how we can implement GCN and graph attention networks. So to start with DeepWalk, let us just quickly brush up our concepts of DeepWalk. So to understand DeepWalk, we must know what basically is word2vec, because DeepWalk and Node2Vec, both of them follows a similar procedure, follows a similar concept as the word2vec mechanism. So a word2vec is basically a mechanism where we can learn word representations. It is for normal natural language sentences. It was not based on graphs. So in the normal word2vec scenario, the input are basically natural language sentences, and the output that we expect are the vector representation for all the words that are present in the input sentences. So, for example, let us take an example. So, for example, let us consider that the input is we are loving this course, and the output that we want is the embedding for the word loving. Now, word2vec can be learned in by using two types of mechanisms. One is skipgram and another is bag of words method. So we'll stick to skipgram in this particular class, because DeepWalk and Node2Vec, they both follow the skipgram kind of mechanism. So in the skipgram mechanism, what we try to learn is that given a particular word, we want to learn the context of that word. For instance, here, in order to learn the embedding for the word loving, the training samples that are created for our deep learning model looks something like this. So we have loving with the word we. So suppose here the window size, that is the number of words we want to consider in the context, is 2. So what we'll do is we'll consider 2 words coming after the target word and 2 words coming before the target word, right? So that makes our window size. So since the word comes in between of our sentence, we have 2 words before it and 2 words after it. So the training sample will be created in that manner only. We have loving, and then the first word in its context, that is we. Then we have loving, that is X, again like the input of the model, loving, and another word that is coming in its context, such as R. Similarly, we have the other 2 training samples, that is this and course. Now, in the word2vec mechanism, what will happen is we'll learn a simple feed-forward network which will consist of one hidden layer. That hidden layer will contain, for example, D number of neurons. If the hidden layer contains D neurons, we'll get a vector representation of size D. So we'll see how it happens. So basically we have this 3-layer feed-forward network, the input, the hidden layer and the output layer. And the aim, the task that we train this feed-forward network is basically to predict the probability of a particular word to occur in the vicinity, in the required window size of the input word. So for example, here for the input word loving, we want the probabilities for the word we, are, this and course to be higher than the probability of all the words that are present in the vocabulary. So using this problem statement and this task, we train this 3-layer feed-forward network, and after we have trained this model, we just take the weights of the hidden layer to be our vector representation for a particular word, right? So this is basically how word2vec works. Now DeepWalk, it follows a similar strategy, but in in word2vec the inputs were basically words, were sentences, but in DeepWalk the input is basically a graph. Now, in order to represent a graph in a way that the words were represented for word2vec, what the authors of this paper, of this method, suggested is that we use something called random walks. So you are already aware what are random walks. So for instance, I've taken this very simple example here. Suppose this is the graph that we are considering, and we want to find out the representation for the node 2. So in this case, what we'll do is we'll create these random walks for this particular graph. So we have these two random walks where 2 is coming in between of the walks. And similar to word2vec, we create these training samples such that the X part of the training samples, the input is true, that is our target node for whichever the representation we want, and the Y part are basically the neighboring nodes based on the window size that we want. So suppose here the window size is 1. So we have the training samples like this, that for the node 2 we have 1 in our vicinity, for the node 2 again we have 3, then for 2 we have 4 and 3 again, based on these random walks. Then we use these training samples to learn a skipgram kind of strategy in order to learn the representation for all the nodes. So now we can see what is happening is basically that the similar meaning words or similar meaning nodes, or like the nodes which capture a similar concept or lies in each other's neighborhood, those will have a representation that is quite similar to each other, whereas different meaning words, or in the case of graphs, the nodes which lie farther apart, they'll have very different representations. So that now how can we decide which representation is similar or different? So we have various different distance measures like cosine similarity or other distance measures, right? So based on those distance measures, if we learn a DeepWalk representation using the skipgram strategy, we can say that similar neighborhood nodes will have similar representation, whereas farther apart nodes will have different representation. Now, how to do that? How to implement it in Python? So what we'll do is we'll just initialize a sample graph. We already know about this karate club graph. We have used this graph in our previous tutorials. So we will use the same graph here and we'll just initialize it in a graph object G. Then what we'll do is we'll use this karate club library, which is basically a helper library for network X, which contains various machine learning algorithms in it. So this library also contains a method for using which we can get the DeepWalk representation. So in order to use this library, we'll first need to install this library. So we'll just do a quick pip install, and once we install this library, then we'll be using this library. So this library is installed, and now how can we use this library? We'll just simply import it, and since we want to use the DeepWalk mechanism of this library, the DeepWalk algorithm from this library, we'll just import the DeepWalk method from the karate club library. Then we import some other helper libraries that we'll need. So we import that, and now how can we use this DeepWalk function basically is that first we need to initialize a DeepWalk model, and to do that we'll just call this DeepWalk method that we have imported from karate club, and we pass some parameters to it. Now these parameters, they basically decide the window size that we want, or the dimensions of the resultant embedding that we want, and so on. So, and also the maximum length of the random walks that we want. So we initialize this DeepWalk method using these parameters, and we here for our for our use we have just set walk length to 100, dimension to 16, and window size to 5. So here for all the 34 nodes that are present in the Karate Club graph, we'll get a vector representation of size 16 for each of the nodes, right? So after we have initialized this model, we need to train this model. So we just call the model.fit function on the graph object that we have, that is the Karate Club graph that we have initialized. Now this to obtain the embeddings from this trained model, we'll just call the get embedding function over this model object. So we have this model.get embedding, and we'll be returned with this embedding object. Now this embedding object, you can see here each of the node, each of this object in the embedding variable, it is basically a vector of the dimension 16, correct? Because that is the dimension that we have specified for the DeepWalk algorithm. Now we'll just store these embeddings in a data frame so that it is easier to access for the further steps that we want to perform. So we just store these embeddings in this df here that we have mentioned. And in order to visualize this embedding, now we see that each node is represented by a 16 dimension vector. Now to visualize a 16 dimension vector is obviously a very difficult task, and it is impossible to interpret it. So what we do is we reduce the dimension of these vectors. So from 16 dimension, we reduce it to a 2 dimension vector by using something known as principal component analysis. So it basically finds out the principal components from the from the big vector, and based on the resultant dimension that we want, it identifies the principal component, the topmost principal components for that number, and then we just map the higher dimension vector into a lower dimension using those principal components. So here we did that only. We initialized a PCA object with resultant dimension 2 because we want to visualize our vectors in a 2D space, and we then transformed all our vectors of dimension 16 into a 2-dimensional space. Then we simply just plot these 2 dimensions that we have now, and after we run this, we can see that this is how our visualization looks. So if you can see here, you can see that the nodes present here like 32, 30, 29, 15, they basically lie closer together, right? Whereas these nodes, that is 16, 5, 6, 4, 10, they lie farther from the 32, 30, 29 nodes but closer to each other, right? So we can see that here we can see that there are 4 kind of clusters that are forming, right? So this kind of visualization helps us to basically see some kind of structure that is present in the graph that might not be seen in the normal if we just normally draw the graph using the networkxdraw function, for instance. Now here we are, the result is that we have is a 16 dimension embedding for each of the node using the DeepWalk mechanism. Now these embeddings can be used for any end task such as node classification or such tasks. Now, apart from DeepWalk, we have another method known as node-to-vec, right? So in this node-to-vec mechanism, it is extremely similar to DeepWalk, but in this mechanism, the random walks that are created from the input graph, they are basically controlled by 2 parameters P and Q. Now in the node-to-vec mechanism, what happens is that the whole algorithm is basically a combination of DFS, that is depth first search, and BFS, that is breadth first search. And these 2 searches, they are regulated by the parameters P and Q. So basically, increasing or decreasing these parameters, it specifies whether we want our representation to be restricted locally. That is, the resultant representation should be able to identify the local structure of the graph, or based on these parameters P and Q, do we want the representation to capture the global structure or global structure of the graph, or for a particular node it should capture the effect of the node that is also that lies farther in the graph, right? So that is the high level intuition of it. We have already seen it in a deeper manner in the theory class. So based on these P and Q parameters, the representations, the random walks are created, and then once we have the random walks, we use a similar mechanism like we did in DeepWalk. We train a simple scriptgram model to learn the final representation, the context-rich final representation. So in order to implement Node2Vec in the Python format, we need a library which has this function Node2Vec. So we just install this Node2Vec library, and we just regulate our GenSim version here so that it is compatible with the Node2Vec library that we want, right? So here it's just initializing. You might need to restart your runtime here. It might happen that we need to restart our runtime here if you are working in Colab and you're installing GenSim like this. See, here it is asking us to restart the runtime. So we'll be restarting the runtime here. And then again, once you have just, here you'll be able to see that the runtime has restarted. If you'll run this, it will already show that requirement is already satisfied because we have, we have already installed these things. Now, once we are done with this, we'll do the necessary imports that we want in order to learn the Node2Vec embeddings. From this Node2Vec library that we just installed, we'll import the Node2Vec function as N2V here. So we'll just import this and other helper libraries that we want, and we will see that all of these are imported, and once it will run, it will import, and then just like we did in DeepWalk mechanism, we'll initialize a sample graph here. So here also we'll take the Karate Club graph that we have already considered in our various examples. We'll just initialize it using the networkx function that provides. And to learn the Node2Vec embeddings, we'll use this N2V function that we just imported from the Node2Vec library. We'll initialize this object using the input graph that we want and the required dimension of embedding that we want. So here again, we are learning a 16-dimension embedding for each of the nodes that are present in the graph. So we initialize this object, and then we learn the embeddings using the dot fit function of this object. Then this dot fit, it basically takes in some parameters in it. So for example, the window size. So here we have just passed the window to be 1. That is, it will just consider the first hop neighbor in each direction for the node. And then the minimum count, basically it like if you look at the word-to-vec manner, so it is essentially learning a skipgram model, right, after the random walks. So if you look at that skipgram model, so a minimum count, it basically represents the least number of times a word should occur in our inputs as to be so that it is considered in the vocabulary. So in the case of graphs, in the case of Node2Vec, this minimum count, it basically represents the minimum number of times a node should occur in a training sample to be considered in the vocabulary, right? And then we have the batch words, which basically tells us the number of batches that we should provide to each of the worker in our this Node2Vec mechanism. So we learn this model and we print this model, and you can see here that it is it is fitting here, and we can see that this is the kind of model that is being learned, that is it is essentially a word-to-vec model with vocab size of 34 because we have 34 nodes, and for each of the nodes we have the dimension 16, and this is like a regulatory parameter. So now the model that is resulted by this node2vec library, this node2vec function, it works, it behaves exactly like how you would how a normal keyed vector that is learned, that the word2vec that is learned by the word2vec mechanism in the GenSim library. This particular model that is learned by using this node2vec library, it behaves in the exact same manner. So in order, since it behaves in the exact same manner, we can use functions like most similar in order to get the node that is most similar to the input node. So for example, here we are providing the input node as 1. So in this particular statement, we want to see the top 10 most similar nodes to the node 1. So we'll just print this and we'll see that the top 10 most similar nodes are 7, 3, 13, 17 with the similarity this. So this is the cosine similarity. So the node 1st and 7th are basically, similar to, up to 98.94% extent, right? And similarly, we have these top 10 most similar nodes. Now again, in order to do a neat PCA representation, we just create this data frame and then again use the same code snippet that we had above to create this PCA plot of the resultant embedding that we are getting from the node2vec mechanism. Okay, so this particular cell is running, and then what we'll do is we'll just quickly compare the resultant representation that we get from this PCA to the PCA that we got from the DeepWalk. So here you can see that the nodes here 4, 10, 6, 5 and 16 lie closer together, 25, 24, 31 lie closer together. And if you just see the PCA that we got from DeepWalk, here we are getting like a similar kind of cluster. So like the nodes 4, 5, 6 and 16, 10, they lie closer together as we saw in this node2vec representation as well. So we can say that a similar kind of representation is being learned by DeepWalk and node2vec. Now essentially both of these methods, they are learning a normal feed-forward network, right? They are learning the representation using a feed-forward mechanism. Now, as we have seen in the theoretical deep learning class, we have seen that in order to capture context, in an efficient manner, in a more appropriate manner, we can use, instead of a normal feed-forward thing, we can use something known as convolutions, right? We have seen convolution networks that are used in the case of images and text in order to learn the context, the local context more efficiently. So we naturally, we want to do something similar for the cases of graph. We want to learn the, the node representation in an even more efficient manner. So what we do is we use something known as graph convolution networks, or GCN in this case. So GCN basically, it's a neural network which uses convolution kind of a thing in order to learn the representation, right? And we have already seen the theoretical aspect of GCN in the class. So in this lecture, we'll see how we can implement this GCN using PyTorch. Okay, so again, so now GCN, since it's a semi-supervised kind of mechanism, it needs an end task. So the end task that we'll consider in our lecture today is of node classification. So you already know that in this karate club graph that we are considering, each node belongs to one of the two clubs, right? So we have two clubs in the whole graph, Mr. High and Officer, and each of the nodes belong to one of these two clubs. So the task that we'll focus on in today's lecture is to classify each node into one of these two clubs, right? So again, we just initialize this network X graph, this Karate Club graph from the network X library. And then what, we'll need to again restart the runtime, wait, because this gensim is now restored to the correct version. Okay, yeah, all right. So now, yeah, so we load this Karate Club graph in this G graph object, and in order to get started with GCN, in order to make our model, learn the node classification, we must start with some kind of initial representation for each node, right? Because in a deep learning model or any computational model, the input is our numbers only, right? And for the node, we want, in order to convert these node to numbers, we need a graph representation kind of technique. So we want to initialize each of these nodes with some existing representation. So we can use normal TF-IDF or normal adjacency matrix representation. But here, since we already know how DeepWalk and Node2Walk works, we are initializing our nodes with the DeepWalk embeddings, right? So this is something that we have already seen. That is the DeepWalk model that is fitted on this graph, and we are just obtaining the embeddings from the learned DeepWalk model. Okay. So we are getting this embedding, and the embedding shape is again 34 cross 16. That is, we have 34 nodes where each node is of the dimension 16. Now what we'll do is, in order to learn this node classification method, we'll need to create a neural network which basically consists of GCN layers, that is graph convolution layers, right? Now, before we do that, we must create a dataset object for the nodes, for the whole graph, right? For all the nodes of the graph. Now, to create this dataset object, what we'll do is, okay, so first, so before creating the dataset, let us first just visualize the DeepWalk embeddings that we have, right? So here we are, instead of PCA, we are using the Tsne plot. So it is another dimensionality reduction mechanism that we have. So we'll use this Tsne plot, and we see that we have, and the color coding that we have done in this plot is basically based on the club of each node. So we see that this red color nodes belong to one club, either Mr. High or so this blue color belongs to officer, and this red belongs to Mr. High. So these belong to two clubs, and we can see that even with the DeepWalk embeddings that we have, these two classes are fairly separable. But can we create a bigger margin, or can we reduce the error in the separation of the two classes? So we'll try to do that with the approach of GCN, right? So again, we just so now what we'll do is, now in order to create so we were talking about creating this data set, right, from our graph. So now in order to create the data set, we'll use this library called PyTorch Geometric. We'll use the same library to implement GCN also. Now to this Python geometric library, it provides us with a few with a few abstract classes basically, which can be used to implement our own data set, right? So now this abstract classes, which like will be using two abstract classes like in-memory dataset and data. So this data class, it basically initializes a graph object for our class, right? For our dataset, and this graph object, the way it is initialized, it needs like an edge index, right? So this edge index is basically a list where the first list represents the source node, and the second list represents the target nodes between which edges are present, right? So if we look at the two inner list element wise, so there is an edge between the between element wise pairs of the two lists, right? So now in order to obtain such an edge list, such an edge index, we simply use the, simply just first get the adjacency matrix from the graph object using the 2 scipy sparse matrix function. And we see here when the adjacency matrix will print, we'll see how it looks like. So it basically looks like an index, which is indexed on a tuple format, which so here you can see that it is like something like this. So we have between the source node 0 to 1 there is an edge, between the source node 0 to 2 there is an edge, and so on, right? So we have this list of tuple indexed variable, where this adjacency matrix or list, it represents something like this. Then we to create the edge index in the format that we require, what we do is we'll extract the rows of all of these so basically the rows of the adjacency, the edge index, will contain the source nodes, right? So we'll extract the source nodes from this tuple of the pairs that we have by using this code snippet, and we just print this row. So we have the first element of each of this tuple, and similarly we'll extract the column, that is the second element from each of this tuple, and we have something like this. Then we'll just stack these row and column together to create this edge index in the format that we want. The first list is basically the source nodes and the second list is basically the target nodes, right? And we just create a tensor out of this. Now, once we have this edge list, what we can do is, another thing that we want are the embeddings that we have learned from the DeepWalk mechanism. So in order to get those embeddings, we'll simply have this embedding.values, because if you remember, we had these embeddings in a dictionary format, right? So we just simply call this embedding.values here, and we have this we stack these embeddings one upon the other, so that we have a matrix of the embedding as well. So this basically this embedding matrix serves as the index for each of the node embeddings. Then we install some of the essential libraries that we want, that is py.geometric, sparse and scatter. So these the installation of these libraries, it takes some time, so you better do it beforehand. So so let it run and we'll see if it is able to install right now or not. Okay. So so after we have these libraries, what we'll do is basically we'll create our own data set using the abstract classes that we have. Okay. So I think our runtime is disconnected. Yeah, it is connected now. Let us just quickly run this. Yeah, so wait. Right. So since it takes some time to load these libraries, we have already installed these libraries beforehand, and now what we'll do is we'll create our own custom data set, right? So from this torch.geometric library, we'll use these two abstract classes, that is in-memory dataset and data. And what we'll do is we'll basically initialize our own class and we call it the karate dataset class, and we have this abstract class that is in-memory dataset in it, right? No, we just inherit from this class. Okay. And then we just simply do the initialization of the superclass and so on. Then for our particular karate club, karate dataset class, we initialize the data of it. So that data is also initialized using this class called data that comes from this PyTorch geometric library, and it takes as input the edge index. We have already created that edge index, so we give that as the input here. And then we initialize some other important parameters that we require, such as the number of nodes, the X part of the of the data, that is the input, that is the embeddings that we have, and the Y part, that is basically the labels that we have, that whether the node belongs to Mr. High club or the officer club, right? So we have data.y, data.x, then we have some number of classes. Since we have 2 clubs, we have the number of classes are 2. Then we simply use this use the train test split function from the from the sklearn library to get a split of the whole data set into train and test split, and where the test size for our case is 30% of the whole data. And we create some train and test masks. So basically these masks, they contains, so it is a list of of size 34, where if a particular nodes come in the training set, that particular value is true or 1, and the rest of it as 0. So we initialize it as all zeros, 34 nodes, 34 zeros, and for each of the each of the node that comes in the X-train part of the data, we put we make the X-train mask for that particular index as true or 1, right? So we have this data's train mask and test mask. Then we have some other functions that are already present in the abstract class, and then we initialize our a data set object using this new class that we have initialized, and extract the data. And now if we just print the data, we can see how it looks like. So this data is basically an edge index. It contains an edge index of each of the 2 classes for these number of edges, and we have the 34 nodes, where each node is represented by with an embedding of size 16, and there are 2 classes, and with the train and test mask of 34 size each. Then we have this now this torch geometric also provides us with these normal GCN convolution layers that we want, right? So we'll just import this convolution layer, and like any other deep learning model that we initialize in PyTorch, we initialize a new class called net, which again takes from the nn.module nn.module abstract class that we have. And we simply do what we simply do is we initialize 2 GCN layers, one after the other, where the first one takes the number of features, whatever the embedding size that we have, and convert it into a size 16. And the other GCN layer, what it does is takes this size 16 and just convert it into the as many number of classes that we have, so that the final classification can take place. Now what we are doing in the forward in the forward part of this class is that we have this X and edge index that comes from the data X and data edge index, and we are providing these 2 X and edge index to this convolution layer, the GCN conv layer, which is then the whatever output we are getting from this layer is passed to the ReLU activation function, so that we are we are introduced with this non-linearity in between. Then after this first GCN layer, we just we extract the representation. Whatever output is coming after this first GCN layer, we are calling this as the representation that we have, and whatever output is coming after the next GCN layer, that is used to perform this classification. We just perform this softmax over this output, and which is further used for classification. Then again we just initialize this net model, and we push it to the device that we want. So we are here right now, we are just using the CPU, so it will stay on CPU itself. Then we'll come to this cell afterwards. Then we just do normal training and testing of this. So in the training part, we put the model to the training, and then we have this optimizer that we have initialized, which is a normal Adam optimizer, which basically basically optimizes all these model parameters with the required learning rate that we are providing. And for each of the outputs that we are getting from the model object, we have something known as the representation and the final outputs. So for this representation, that is the embedding that we have, we are saving it in a variable known as GCN embeds, and we save it in a NumPy format, right? Then we have this, then finally we compute the loss between the training, the ground truth of the training and the representation that we're obtaining from the from this model, and based on this loss we are optimizing, we are doing this optimizer step that basically changes all the weights based on this loss. Then again in the testing part, we're just calculating the training and testing accuracies that we're obtaining. So now if you just run it, you can see here that we are getting a train accuracy of 1. So it is a small data set of only 34 nodes, and the GCN is able to learn it in a well manner. So we are getting a training accuracy of 1 and a testing accuracy of 0.9. So now when you do this TSNE plot, so initially the TSNE plot that was looking something like this from the DeepWalk embedding. Now if we are plotting this TSNE after the GCN learning, it is looking something like this. So as you can see, the nodes with the same class are now clustered even more together. The last thing that we'll see today is the graph attention network. So that is extremely similar to GCN. So we have already seen the theory of it, but for the for the implementation point of view, Torch or Geometric provides us with the graph attention layer as well. So we just simply import this graph attention layers, and instead of GCN that we had imported before, we simply use this graph attention layers here, and rest of the things remains same, right? So we just have this new model now, that is NetGAT, and we instead of GCN we have this graph attention layer. We use the exact same thing where we initialize this model, and then the training and the testing loop will remain the same. And then again we just plot this, and we can see that a similar kind of structure is taking place where the two classes are well separated. So yeah, so this was all about graph representation learning and how we can implement it in PyTorch and Python, and we'll see and you should just go and explore more of these methods on your own. So yeah, thank you.